So accelerated motion graphs generally break down into three categories. You got dt graphs, vt graphs, and at graphs. We mean for dt, it's distance or displacement and time graphs. For vt, it's velocity time graphs or speed time graphs. And at would be acceleration time graphs. So one of the most common forms of an acceleration graph for dt is the smile here. And what I'm going to do is, to help you conceptualize this better, I'm going to draw a dotted line in the middle of this so that you can kind of see the smile graph as in two parts. This dt graph for accelerated motion is what we call the smile. And essentially, if you see any part of the smile, whether it's the downwards portion here that turns into the smile, or the upwards portion of the smile, either way, that indicates positive accelerated motion. Now, when we look to the right side of the graph, that might make a lot more sense because you're looking at, this part and like, well, it's clearly going up. And so, it's got to be positive acceleration. But how is this part positive? Well, first of all, remember that this is a curve, right? So it's an exponential function, which means that, in general, trends are a little harder to predict, a little bit more complicated. But also it has to do with the tangent lines. And I'll draw a couple of tangent lines to show you what this means. Now, a tangent, although this is really a calculus term, is a slope that goes through a point on a curve. And so you got a giant curve here, and we take more than one tangent because there's more than one part of the curve here. I took 3 points and I drew a tangent line through them. And so what we see is that when we take 3 different sections of the curve, right, the half of it that's going down, the tangent slopes become less negative. And eventually, over here, in the middle, you could say, it actually goes to 0 and then keeps going upwards. So if they become less negative, that's another way of saying more positive. And so, therefore, it is a positive accelerated motion. Other synonyms for positive acceleration would be words like speeding up or increasing speed. And so any part of the smile over here would be speeding up or increasing speed. Now, in the case of the left side here, it would be speeding up in the positive direction. So, you were traveling west and now you're speeding up towards the east, or so that you reach the east. And so it's eventually turning the other way. Now, this common curve for accelerated motion on a dt graph is known as the frown. And this represents a negative acceleration no matter which half of the frown we're talking about. Yes, that even means this one. Now, much like in the previous, if I were to take random points right along the curve and then, like I did previously, draw tangent lines, right, that pass through the curve, pass through the points, I would see that my slopes get smaller and smaller once again. And what we mean when we say that is that they get less positive. And in fact, when we're talking about this portion of the frown, we're specifically referring to an object that is slowing down, okay? And by having a less steep slope or less positive slope, that is slowing down to a stop. When we look at the top of the hill over here, that has a slope of 0, which means that this is stationary or not moving. Now, this portion of the graph is just really the object accelerating in the opposite direction that it was once going in. So let's say it was traveling It was coming from the east, then it stopped, turned around, and then accelerated towards the west. This could also be an object that was thrown upwards until it at one point slowed to a stop at its max potential energy and then started free falling back down. Either way, this represents a negative acceleration. Now on a VT graph, constant speed looks like a horizontal line, and that's because it comes from the slope of a DT graph. So let's say, for example, that the slope of the DT graph is 5. Well, then you'd look for the value of 5 on your VT graph here, and you would draw a horizontal line for however long the DT graph from before went on. And this would be constant speed of 5 meters per second. Now, let's say, because remember that your velocity can be negative. Because velocities can be negative due to the direction, if we have a slope on the previous DT graph that is -3, we could simply go below the 0 line here, find -3, and then draw, once again, a horizontal line for however long that graph went on for. Let's say the previous DT graph had a smile, which would indicate acceleration. Well, if it's a smile, then that's positive acceleration. On a VT graph, that would translate to be a line that slopes upwards, much like this. And I'll highlight this here so that we can see it a little bit better. So this would be a positive acceleration. And remember that the slope of a VT graph is going to give us the value of acceleration. If the DT graph previous showed negative acceleration, right, or slowing down, then your graph, or the VT graph, would be a line going downwards indicating negative acceleration, and I'm going to just highlight that in orange as follows. So let's say I want to take this line here and I want to translate to a VT graph and then an AT graph. Well, I have the coordinates here at 3 and 3. So remember that the slope of a DT graph is equal to the speed or velocity. So for the slope, it's going to be the rise over the run, or the change in y over change in x. And in this case, that'll be 3 over 3, which would equal to what? Well, then what I would do is I would take that value of 1. I'd go and find 1 on the VT graph. And then for 3 seconds, I'd draw a straight line at 1 because that would be a constant velocity. Now, on an AT graph, if the velocity is constant, like it is over here, then that means the acceleration is 0. So then for 3 seconds, I'm going to have an acceleration with a value of 0 here. Let's say on the next part of the DT graph's motion, we have an object that is speeding up, or the same object that was going at a constant speed is now speeding up. Well, that curve would mean that you would have a positive acceleration. So from the 3 on the VT graph, we would draw a straight line to the like of this. And so you'd have a slanted line on the VT graph when there's a curve on the DT graph. And if the curve is part of the smile, then you'll have a slanted line that has a positive slope. Now, let's say we took the slope of this graph and we said that, it's about, and of course we're just doing the rough calculation. Let's say we say that it's about 2 meters per second squared. Okay. So the slope is 2 meters per second. Well, then what you would do is you would go to the 2, where the acceleration graph is, and for that same time of about 3 seconds, you draw a straight line at the 2, indicating constant acceleration. So we're going to write constant, and we're going to write positive acceleration. So let's say we're given a DT graph here with different types of lines in it, and this describes the object's motion over a certain time interval, in this case 13 seconds. Well, you got to break it off, you could say line by line or portion by portion. So when I look at the blue line, I can see that it is going at constant speed. So from 0 to 3 seconds, it's constant speed. Right? And sometimes I draw a dotted line to kind of help myself see it a bit. So if I do the same with the second time interval, it'll go like this. I can see that it's speeding up, right? Or accelerating in the positive direction because I got part of the smile there. Now, if I look from 6 to 10 seconds here, I got part of the frown, which means it's either slowing down. In this case, because it seems to be curving upwards, it's slowing down to a stop. And then when I look at the last portion, and that's from 10 to 13 seconds here, well, it would have a slope of 0 if I were to take the slope. So because it has a slope of 0, we're going to say it would have a speed or velocity of 0. So that really is the same thing as saying that it's not moving or stationary.